Okay, continue on. So we just checked, and then I write down here, note integrals, antiderivatives, and derivatives are opposites. They undo each other. You can always check your integral by differentiation. If you differentiate your integral answer, you should get the original integrand. Always. So our next rule, what to do about exponents. The integral of x to the n dx is 1 over n plus 1, x to the n plus 1 plus c, for n not equal to -1. Doesn't work for -1. To find the antiderivative or integral of a variable raised to a numeric exponent, we already did this once, but it's important. Not 1, you increase the exponent by 1, then multiply by the reciprocal, the new exponent. Variable raised to numeric exponent. So integrating this guy. In here, I just wrote this 2 ways. You'll sometimes see it like this when the numerator of a fraction happens to be 1. Sometimes they'll plunk the differential on top. It means this, so don't get worried about, oh, they put the dx on top. That's just them saving a little space. But like we said before, if you can get rid of a fraction by using a negative exponent, get rid of a fraction by using a negative exponent, and then we don't particularly like radicals. And then it's the same rule. Increase the exponent by 1. -1/3 plus 1 is 2/3. Multiply by the reciprocal of the new exponent. Then I throw on the plus c. And then these things check by differentiation. The 3/2 just hangs out there. Multiply by the exponent. Decrease the exponent by 1. The derivative of that plus c would be 0. We get x to the -1/3, which is 1 over the cube root of x. And there's that one. Okay, next basic rule. The integral of k times f of x dx is k times the integral of f of x dx, that you can factor out numerical coefficients, or for coefficients, just write them down and don't worry about them. Just the same as it is in differentiation. If it was pathetically simple in differentiation, it'll be pathetically simple in antidifferentiation. 4. The integral of f of x plus or minus g of x dx is the integral of f of x dx plus or minus the integral of f of g of x dx. You can split up integrals by adding or subtracting. Remember, the same is not true for multiplication and division. For differentiation, you were told to either simplify or use the product and quotient rules. So since it was special and complicated in differentiation, it'll be special and more complicated in anti-differentiation. If it was hard in differentiation, it's going to be harder in anti-differentiation. Then all the trig things. Again, the important thing one of the important things you want to remember here is that when my argument is linear, mx or even mx plus b, the effect of that slope, when I anti-differentiate each and every time, is going to be a 1 over m. And you're going to have these linear arguments so many times, it's just easier just to memorize that the effect of that slope when I integrate, when I anti-differentiate, is to divide by, is to multiply by the reciprocal. Otherwise, it's just your trig derivatives turned around. Each time you're asking yourself, what has a derivative of? What has a derivative of cosine? That is sine. What has a derivative of secant squared? That is tangent. What has a derivative of secant tangent? That is secant. Where it gets a little confusing is you got to remember the SIGNs kind of turn around on you. What has a derivative of positive sine? That's going to be negative cosine. What has a derivative of positive cosecant squared? That's going to be negative cotangent. What has a derivative of positive cosecant cotangent? That's going to be negative cosecant. Then my angles never change, and the effect of that slope is to divide by it. My exponentials, e to the mx. Again, those linear arguments, in this case a linear exponent, the effect of that slope is to divide by it, and since e to the x, when I differentiate it, repeats, when I integrate it, it's going to be repeat. And pretty much the same thing with the general exponential. When I differentiate the general exponential, I end up multiplying by the natural log of the base. So when I integrate, I'm going to divide by the natural log of the base. The integral of 1 over x dx is the natural log of x. Again, depending on how particular we're going to be, maybe we'll slap absolute value around it. I'm not going to stress too much about that. If the computer wants absolute value, give the computer absolute value. The integral of 1 over the square root of 1 minus x squared is sine inverse. Again, it's just your derivative statements turned around. The derivative of sine inverse is that, so the integral of 1 over the square root of 1 minus x squared is sine inverse. Same thing here, the integral of 1 plus 1 over x squared is tan inverse. Again, it's just your derivative statement turned backwards. The derivative of tan inverse is 1 over 1 plus x squared. So then the integral of 1 over 1 plus x squared is tan inverse. Then more generally, and we're not going to prove these things, you're just going to accept them as truth. If I don't have a 1 there, but have some other constant, a squared, how that is going to affect the derivative, or the integral, is that that's going to be sine inverse of x over a. So you're just going to have to remember that the square root of a number minus x squared is going to be sine inverse x over a. And the same thing here, 1 over a squared plus x squared. Again, it's almost that format, but instead of 1, I have a different number here, a squared. The answer there is going to be 1 over a tan inverse x over a. And so that somehow, we're not going to prove these things, we're just going to accept them as facts because they are going to be a little more general. They're not necessarily going to have 1s there, they're going to have some other number. And so a squared gives us an x over a in the argument of both of them, and in the case of the tangent inverse, a 1 over a. So let's do a few problems, then we'll be done with this section. Evaluate the following. So now we're using our new notation. And you see the integral sign, you see the dx. That is our notation. Is telling us to find the antiderivative, to find the indefinite integral, find the most general antiderivative, find the indefinite integral, whatever word you look like, whatever phrase you like, but it's telling us to integrate, telling us to anti-differentiate. But it is a product. And our only choice that we have right now is that we have to multiply it out first. Must multiply out first. If you don't do that, if you just decide that you can do the x to the negative 3 and then do the polynomial that's following it, that you can just do them separately, you will lose all the points. Products and quotients were special in differentiation. They are special and harder in anti-differentiation. Now, when I could just multiply it out, it's not going to be a big issue. But if I can't multiply it out, it's a huge issue and has to be acknowledged. And so you've got to multiply out your products first. You absolutely have to. If you don't, you will lose all the credit until we learn other ways to deal with it. Then once you have the other ways, you've got to do one of the other ways. But you must do something that acknowledges you have a product. So I'm going to multiply this out first, remembering to add my exponents. And I'm going to rewrite that just a little bit more to remind us that 6x to the negative 1 is the only exponent that we are not going to use our exponent rule for. Negative 1, we're going to remember, is 1 over x, and we're going to rewrite it as such. And now I have it in a nice, perfect, simplified form that's still the original problem, but it's in a format that I can deal with better. And so I can do it piece by piece. Increase the exponent by 1, multiply by the reciprocal of the new exponent. The integral of 1 over x is natural log of x. Increase the exponent by 1, multiply by the reciprocal of the new exponent. And so I've got 4/3 x cubed plus 6 natural log of x plus 1/2 x squared plus c. And then I can check these things by differentiating. So let's check it. I take my answer and I differentiate it. And it has to get me back to the original integrand. So differentiating. And the derivative of that plus c on the end is 0. And so I get 4x squared plus 6 over x plus, or I don't need the plus 0. And there we go. And you can check it. It checks back to this line right here, basically. It's not going to check all the way back to where I multiplied it out. It will check back to whatever line was just before you did your antiderivative. So right here is where I did my antiderivative, so it checks back to this line. There is no good way to check your work from here to here other than to be careful and check your work again. And so there we know it's right. Now I want to make a little comment. When we did this, when we had 6x to negative 1 dx, we said that that was 6 times 1 over x. We said that was 6 times 1 over x dx, which was 6 times the natural log of x plus c. That's the correct way. But I will have people try to use the exponent rule. Why can't we use this? The x to the n dx is 1 over n plus 1, x to the n plus 1. Then I'll have lots of people that want to use that exponent rule for every single exponent in the world. There's one exponent that doesn't work. It doesn't work for this one. Now let's try it. Try it. So that 6 is just going to stay there. So I would increase the exponent by 1 and then multiply by the reciprocal of the new exponent. And so that would give me 6 times 1 over 0, x to the 0 plus c. And there's the huge problem. That's undefined, and there's why we can't use it. That rule's just not going to work when my exponent's negative 1. And so you really have to remember that there's one exponent that we have a special rule for, that x to the negative 1 is 1 over x, and then because the derivative of the natural log of x is 1 over x, the integral of 1 over x is natural log of x. So you got to remember that when you have x to the negative 1, your exponent rule isn't going to work. And let's end this video.